Hi everyone, today we're covering topic 9.4, thermodynamic and kinetic control. So we know from the previous lesson, if delta G is less than 0, that means that a reaction is thermodynamically favored. In other words, it occurs without an additional force. But despite that, the reaction may still not occur. And the reason for this is because the reaction might be under what's known as kinetic control instead of thermodynamic control. And I'll explain that a little more in the next slide. So let's take graphite versus diamond. Both of these, at the end of the day, are carbon. They're what are known as allotropes of carbon. They're just carbon in different orientations. You can see graphite here makes these hexagons that stack on top of each other, whereas diamond has this more cubic structure with a different kind of crystal on the inside. And so a diamond is a strong covalent network solid. Graphite, on the other hand, is a weaker covalent network solid. So diamond, as you can see, is a really, really ordered structure, and so it has a low entropy. In other words, it's really, really ordered. But graphite has a higher entropy. In other words, the preferred reaction, or the thermodynamically favored reaction, is to go from diamond to graphite because of this entropy. But obviously, at room temperature, diamond doesn't turn into graphite. And the reason for that is that it's under kinetic control. And so there's too much, or at least the activation energy, for the reaction to occur is too high. And I explained that down here in kind of graphical terms. If you remember before, we have these reaction coordinates. And let's say on the side here, I have G, right, the amount of free energy. In a thermodynamically favored reaction, what would happen here is that the energy of the reactants is going to be higher than the energy of the products. In other words, delta G is going to go down, so delta G is less than 0. But in the diamond example, this is the diamond example, right, the free energy of diamond is going to be a lot higher because it has a really low entropy, and so it's going to have a higher free energy as a result. And then to make graphite, so here's diamond, here's graphite, you'd release a lot of that entropy, or at least your entropy would go up, and so that would be favorable to go in that direction. So delta G should be negative. But what happens is you have such a high barrier, and I'm going to draw it so high that it goes off the graph. You have such a high barrier that, right, this activation energy is too high. In other words, yes, the reaction is thermodynamically favored, but because it takes so much energy to break that activation barrier, the reaction isn't actually going to happen. And so that is what being under kinetic control is. And so we'll see a lot of examples of this where a reaction might be thermodynamically favored. In other words, delta G is less than 0, but activation energy is still too high. And so the reaction does not happen. So let's look at this practice problem right here. We have this combustion of ethanol, C2H5OH plus oxygen is going to make CO2 plus H2O. And it gives us two different potential energy diagrams. One where we have a really low activation barrier, and one where the activation barrier is higher. But you can see this difference in products and reactants is pretty much the same in both. We're given delta S and delta H, and so from this, we can probably calculate delta G. It's equal to delta H minus T delta S. Delta G, and we're told this is at 25 degrees Celsius or 298 Kelvin. Delta G is going to be equal to, delta H, we have to be careful, this is in kilojoules, so we should multiply that by 1,000. It's going to be negative 1,235,000, yep, joules per mole times Kelvin, minus 298 Kelvin. That is times 217.7 joules per mole Kelvin. When we do the math, we get negative 1,299,874 joules per mole. And I apologize, this should actually be just joules per mole. The units for enthalpy do not have Kelvin on it. But that's negative 1,299,874 joules per mole, which is negative 1,299, we'll round up to 230 kilojoules per mole. That's what delta G equals. So it's less than 0, so it should be spontaneous. With that, we can look at these answer choices now. We're essentially asked which of the following diagrams above would best help explain the low yield of the reaction. Essentially, the reaction is not favored. So obviously, delta G is less than 0, so we know that thermodynamically, it is favored. And so that's not going to be a reason. So if we look at diagram 1, it says it represents a reaction that is not thermodynamically favored. Of course, we calculated delta G is less than 0, so this cannot be true. The second one says it represents a reaction that reaches equilibrium quickly after a very small amount of the reactants is consumed, but we can't actually tell from the diagram, so that is not true. We can't tell anything. We can't tell equilibrium from those diagrams. We also know that delta G is less than 0, so it can't reach equilibrium because this means delta G equals 0. So that one can't be true. C says diagram 2 because it represents a reaction with a high activation energy for a molecule to overcome and a very slow reaction rate, even if it is thermodynamically favored with delta G less than 0. And diagram 2 basically says the exact same thing, that it's thermodynamically favorable with delta H less than 0, but the product form are unstable and quickly revert back to form reactants. This one doesn't really make sense because the products are lower energy, and we don't really tell thermodynamic favorability from delta H. We do that from delta G. So the only answer here is C, right? This activation energy is really high, and so it's under kinetic control. We'll discuss this a little bit more in class, but for now, that's all. Thanks, guys.